A strange shape has appeared inside the frozen landscape of East Antarctica. It resembles a giant hummingbird with a narrow head, outstretched wings, and a long tail carved across the ice. From space, the pattern looks almost artificial, but it was not drawn by people, and it is not visible in ordinary satellite photography. It emerged when one of the most powerful Earth-observing radar systems ever launched looked through the bright surface of Antarctica and revealed how an entire river of ice was being torn apart by a mountain hidden in its path. The image came from NISAR, the NASA-ISRO synthetic aperture radar satellite. Launched in July 2025, the joint American-Indian mission was designed to measure changes across Earth's land, forests, wetlands, glaciers, ice sheets, and crust. Unlike a normal camera, NISAR does not depend on sunlight. It sends microwave radar signals toward Earth and measures the energy reflected back, allowing it to observe the surface during darkness and through clouds. That capability is especially valuable in Antarctica. The continent experiences months of darkness, frequent cloud cover, blowing snow, and vast areas that appear almost completely white in visible light images. To the human eye, the surface can look empty and uniform. Radar sees something very different. It detects variations in roughness, structure, moisture, ice orientation, and the way signals scatter from within the snow and ice. The hummingbird pattern formed around a mountaintop called Nunatak Zadarjavshestia in East Antarctica. A nunatak is a rocky peak that rises above the surrounding ice sheet or glacier. Most of the mountain may be buried, with only its upper portion visible. In this case, the ice is flowing northeast toward the ocean when it encounters the obstruction. Like water moving around a rock in a river, the ice must divide, accelerate, deform, and reunite around the mountain. Glacial ice may look solid and motionless, but over long periods it behaves like an extremely slow fluid. Gravity pulls it from the high interior of Antarctica toward lower ground and the coast. Some sections move only a few meters each year, while fast ice streams can travel hundreds or even thousands of meters. When the flowing ice meets uneven terrain, different parts begin moving at different speeds and directions. That uneven movement creates stress. Ice can bend and deform gradually, but it has limits. When the stress becomes too great, the surface fractures into deep cracks known as crevasses. In NISAR's image, these fractures appear as sharp green lines surrounding the mountain. Their position reveals how the ice is being stretched and pulled apart as it flows around the rock. The hummingbird is therefore not a single object buried beneath the ice. It is a visual map of movement, texture, and structural damage. Its apparent wings and tail come from different radar responses produced by smooth ice, fractured surfaces, snow layers, and the exposed or partially buried mountain. Scientists created the image using signals with different polarizations, meaning the radar waves vibrated and returned in different orientations. NISAR transmitted horizontally polarized radar waves toward the surface. When those signals returned, some remained horizontal, some became vertically polarized, and some produced a mixture. Each response carries clues about what happened to the wave. A relatively smooth surface may reflect energy differently from a field of jagged crevasses. Signals may also penetrate dry snow and scatter from structures beneath the immediate surface. Scientists translated these radar responses into color. The colors are not what someone standing in Antarctica would see. They are a scientific visualization of how the microwave signals interacted with the ice. Areas with different combinations of scattering appear magenta, green, or white. The brilliant pattern allows researchers to separate features that might otherwise blend together in an ordinary photograph. When the same location is viewed in optical light, the hummingbird almost disappears. The landscape becomes an expanse of white snow and ice. Faint shadows reveal the mountaintop, while subtle ripples suggest the surface is not completely smooth. But the network of fractures and the complex flow pattern are far more difficult to distinguish. Radar transforms that visually simple scene into a detailed record of forces acting on the ice. The image is visually remarkable, but its scientific importance extends beyond one mountain. Antarctica contains enough frozen water to raise global sea level dramatically if large amounts of its ice were transferred into the ocean. Scientists therefore need to understand not only how much ice exists, but how it moves, where it accelerates, and which regions are becoming unstable. Ice does not disappear only by melting at the surface. Glaciers and ice streams carry enormous quantities of ice toward the coast. Once ice moves from land into the ocean, it can form floating shelves or break away as icebergs. The speed of this movement influences how quickly Antarctica contributes to sea level rise. The landscape beneath the ice plays a major role. Mountains, ridges, valleys, and basins can slow ice, redirect it, or channel it into faster streams. Some features act like obstacles that resist motion. Others create pathways that allow ice to accelerate toward the sea. Because most of Antarctica's bedrock is hidden beneath kilometers of ice, satellites and aircraft are essential for understanding how the frozen continent behaves. NISAR was built to observe these changes repeatedly rather than produce only a single picture. The satellite can image global land and ice-covered surfaces on a 12-day cycle, with more frequent average revisits when ascending and descending orbital passes are combined. By comparing observations over time, scientists can measure movement and surface deformation, in some cases detecting changes as small as centimeters. Repeated radar images can be combined through a technique called interferometry. Scientists compare the phase of radar signals collected from nearly the same position on different dates. Tiny differences reveal whether the ground or ice moved toward or away from the satellite. This approach can map glacier flow, earthquake displacement, volcanic swelling, landslides, and land subsidence. That means the hummingbird image is also a demonstration of what the mission may accomplish across the planet. NISAR has already been used to examine earthquake-related ground movement, sinking land around Mexico City, volcanic landscapes, agricultural areas, and ice-covered regions. As more data become available, researchers will be able to build long-term maps of how Earth's surface changes. The satellite carries two radar instruments. NASA provided an L-band radar with a wavelength of about 24 centimeters, while ISRO provided an S-band radar with a wavelength of about 9.4 centimeters. Different wavelengths interact differently with vegetation, soil, snow, and ice. Combining them gives researchers more information than either system could provide alone. The satellite also uses a large radar reflector antenna and a technique designed to collect high-resolution measurements across a wide strip of Earth. Its observation swath is greater than 240 kilometers. That balance between detail and coverage is important because many environmental processes occur across enormous areas. A satellite that sees only a narrow strip may miss the wider system, while one that sees the entire region without enough detail may fail to detect subtle movement. NISAR's information is being made openly available. As of July 20, 2026, the public could access data from both radar instruments as teams in the United States and India continued releasing processed products. This allows scientists, governments, emergency managers, students, and independent researchers around the world to use the measurements without having to operate their own satellites. For disaster response, repeated radar coverage could help map ground movement after earthquakes, identify areas affected by landslides, and detect deformation around volcanoes. For agriculture, the radar may help monitor crops and soil moisture. In forests and wetlands, it can reveal structural and environmental changes even beneath cloud cover. Across Greenland and Antarctica, it can measure the movement of ice that directly affects future sea levels. The Antarctic hummingbird captures all of these possibilities in a single image. A normal photograph shows a nearly featureless frozen surface. Radar reveals a mountain resisting a moving stream of ice, fractures spreading through the surrounding terrain, and complex internal structures encoded in color. It also changes the way Antarctica is imagined. The continent is often portrayed as static, silent, and permanently frozen. In reality, it is moving continuously. Snow accumulates in the interior. Ice compresses under its own weight. Glaciers flow around buried mountains, through deep valleys, and toward the coast. Cracks open, shelves flex with tides, and icebergs break away into the ocean. NISAR cannot prevent glaciers from retreating or stop sea levels from rising. Its value comes from revealing changes early and measuring them accurately. Better observations reduce uncertainty. They allow scientists to distinguish temporary variations from long-term acceleration and identify which regions deserve the most attention. The hummingbird itself may never be visible to anyone standing on the ice. It exists as a pattern created by radar waves, polarization, flowing ice, and a mountain rising through the frozen landscape. Yet it represents something real, enormous forces reshaping Antarctica beneath a surface that appears calm. A mountain interrupted an ice stream. The ice fractured around it. A satellite hundreds of kilometers above Earth detected those fractures and transformed them into the outline of a bird. What looks like frozen artwork is actually a map of a continent in motion, and one of the clearest demonstrations yet of how radar is allowing scientists to see a version of Earth that ordinary cameras cannot.